right, we're going to walk our way through the proof of the small gain theorem. So basically, the small gain theorem starts with an uncertainty set. Okay, in this case, our uncertainty set our delta has infinity norm less than 1 over gamma. Okay, so that's our uncertainty set. Suppose P is stable and gamma is positive definite. I'm sorry, just a positive scalar. Then the closed loop system is well posed and internally stable. If for all delta if and only if for all delta in the uncertainty set, we have this. Okay. So notice here, this is an if and only if condition, which means we have two directions we need to prove. We need to prove both directions of this. So the small gain theorem is both necessary and sufficient. Okay, so it's necessary and sufficient because we're talking about it has to work for all uncertainties in the uncertainty set. Now, where conservative often comes in is when we have a specific uncertainty. We're not trying to solve it for all uncertainties in the uncertainty set. We have a specific uncertainty that we're dealing with, and so that specific uncertainty is actually a restriction on this uncertainty. And so that can actually, we could actually have a system that's stable in that case, even if this condition is not satisfied. So we have some of those kinds of things. All right. So that's the small gain theorem. So we're going to look at the proof of this. We assume without loss of generality. So we'll see that sometimes you'll see that in various proofs as people prove them without loss of generality. So for now, we can assume that gamma is equal to 1. Otherwise, we can scale both delta and P by gamma appropriately, and so that we basically have gamma is equal to 1. So we can assume that gamma is equal to 1 and everything goes through. So assume now that P and delta are both stable and the infinity norm is strictly less than 1. Then P and delta, the product, is also stable. The closed loop system then is stable if and only if this determinant has no root in the closed right half plane, that is, in the right half plane plus the axis. Okay, for all delta in the uncertainty set. Okay, so really this is the condition, and remember this is the well-posed condition that we had seen before, well-posedness. So here we say is stable if and only if. It's also, we can also say it's stable and well-posed. Okay, so we could have added that here. Stable and well-posed if and only if this condition has no root in the closed right half plane for all delta in the uncertainty set. Okay, so if it has a root in the right half plane and the axis, if it has a root in the closed right half plane for some delta, then our closed loop system is not guaranteed to be stable. Okay, and the bottom line is, in that case, we can find an uncertainty that will blow us up. All right, so that's the issue. Now, since the infinity norm is strictly less than 1, the uncertainty is less than or equal to 1, then for any delta in the uncertainty set, that looks something off. Anyway, we have that 0 is less than 1 minus P infinity, right? That comes from this inequality. And this inequality, I have 1 minus P delta infinity norms. So because of this, that's where this inequality comes from. And the reason the inequality goes this way is because we're actually looking at the negative of this. Okay, so this quantity is actually greater than or equal to this quantity, but when we take the negative, then this quantity is greater than or equal to that quantity. Okay, so we just are building our inequality. So we have this quantity, 1 minus P delta infinity. So this is actually more of what's needed rather than this, but this is in some ways, easier to work with. So this quantity is equal to 1 minus the supremum of the largest singular value of that product over all S in the right half plane. Okay, so here we're doing this. So the supremum then is over all S in the right half plane, including the imaginary axis. Now, the supremum is again like the maximum. If I took the minus sign inside of here, then we would work with the infimum. Okay, and instead of the largest singular value, we would work with the smallest singular value. So this quantity is actually, we say less than or equal to. Really, it should be equal the infimum of S in the right half plane of this quantity. Okay, so this quantity is greater than or equal to 0. Okay, this quantity is, so the smallest of the singular values of I minus P delta is greater than, strictly greater than 0. Strictly greater than 0. Okay, so what is this? What is the importance of this? Well, remember, I plus P delta, we need the determinant of that to be non-zero for all S in the right half plane and the imaginary axis. If the smallest singular value and the smallest value of that over all frequencies is positive, okay, then we cannot have zero determinant, right? We cannot have zero determinant. So this tells us that the determinant is not 0 for all S in the right half plane. Okay, so we started off with our system being stable and the infinity norms being what they need to be, and that tells us that this determinant cannot be 0 for all S in the right half plane and for all uncertainties in our uncertainty set. Okay, so we've proven one direction. Now we're going to prove the other direction. And we will show this by contrapositive argument. We assume that there is some delta in our uncertainty set such that the closed loop system is well posed and stable, but that the stable system has infinity norm greater than or equal to 1. Okay, so by making these assumptions, we will show that the closed loop system cannot be stable. So that's the contrapositive argument. Now, since the infinity norm is greater than or equal to 1, then there is a frequency at which the supremum occurs of this. So remember, the infinity norm is the supremum over all frequencies. And so if this is greater than or equal to 1, then there is some frequency at which that supremum occurs. So there's actually the largest singular value. There is a frequency at which this supremum is achieved. Okay, and so if we look at a singular value decomposition of the P at that frequency, we have a U. So U and V adjoint are both unitary matrices. This is going to be a singular matrix of singular values, diagonal. Okay, so we have some diagonal values, singular values. And so the infinity norm is the largest singular value of this over all frequencies. So that's sigma 1. So that's actually the supremum of sigma 1. And that, again, that's going to be greater than or equal to 1. So here, sigma 1 occurs at the frequency omega naught. Okay, so that's the largest singular value. So that's the norm. And so associated with the largest singular value are the singular vectors v1 and w1, or I'm sorry, v1 and u1. And so these are the singular vectors associated with that singular value. And so we've seen using matrix perturbations that we can define an uncertainty this way. Okay, so this is an uncertainty matrix of proper dimensions, and the infinity norm of, or rather the notice that this is just a constant. Okay, so this is just a constant matrix. It's not a transfer function per se. We can make a transfer function out of it, but there's no point, no reason to. We can just make it a constant, because a constant is a special case of a transfer function, and this particular matrix is a special case of matrices. It's a rank 1 matrix, right? This is a column, this is a row, so we have this. So since sigma 1 is greater than or equal to 1, then this quantity, which has sigma 1 in the denominator, is less than this quantity, which is the numerator. Okay, so that's where the less than or equal to. But this quantity, because of the fact that these are singular vectors, this quantity has norm 1. Okay, both of these vectors are unit vectors. They have unit norm, and so the norm of this product is actually 1 as well. So we have this situation. So here we have an uncertainty less than or equal to 1. Okay. We have the uncertainty less than or equal to 1 and a frequency at which that uncertainty occurs. So actually I asked why, but I've already just told you why. All right. So with this uncertainty at that frequency, we have this relationship. 0 is equal to the determinant of 1 minus. So notice that this quantity has norm 1. Okay. But this quantity, so if I take this quantity and multiply by p of j omega, actually the norm of p of j, so this p of j omega, which has our singular value decomposition, we can show that this quantity here, so this is the singular value decomposition, multiplying on the left by this and on the right by this, actually neutralizes this quantity. So this quantity becomes it becomes a column of the identity matrix, actually the first column of the identity matrix, and this quantity here becomes the first row of the identity matrix. So when I multiply these three things together, it picks off the 1, 1 element of S. The 1, 1 element of S is in fact sigma 1. So 1 minus 1 is what we have here, and that's a scalar, that's 0, and the determinant of that is 0. So that's where this part of the equation comes from. Okay. Since for any matrix, whenever I have a product here and an identity, so this is a 1 by 1 identity, I can rearrange the order of these matrices and still maintain the determinant. So this is equal to this determinant where I have moved U1 over to the other side. Okay, so by doing that, I get this determinant. So these two determinants are equal to, and again, that's just a property of determinants. So this times this is delta. This is P. Okay, and so what this shows is that 0 is equal to the determinant of I minus P evaluated at j omega, delta at j omega. So we have 0 determinant. This means that the system is either not well posed and or not stable. So this provides our contradiction, and as a result, we have proved the small gain theorem. Thank you very much.